Hey, our first topic is limits. Limits are fundamental to everything that we do in calculus, so very important to get a great understanding of limits. So today's video lesson is going to just focus on getting the concept of what is a limit. Later on, we'll look at how we compute them, but for now, we're just going to try to understand what they are. We're going to look at them numerically, algebraically, and graphically, and there'll be a definition or two thrown in there as well. All right, let's start. Suppose I told you that for some function f of 2 is equal to 6. You put 2 into the function, and out comes a 6, whatever the function might be. And for that same function, f of 2.5, 2.5, is equal to 6.5. And it turns out that f of 2.9 is equal to 6.9. And suppose I told you that further, f of 2.99 is 6.99, and f of 2.9999 is 6.9999. And what's happening here is I'm choosing x values that are getting closer and closer and closer to 3, but still less than 3, and seeing what happens to the y values, the function values. And if you had to guess, you would probably guess that as the x values get closer and closer to 3, the y values get closer and closer to 7. Just a guess. And this is the concept of a limit. And in particular, it's what we call a one-sided limit because we're only approaching 3 from the left. And we say the limit as x approaches 3 from the left of the function f of x is equal to 7. We don't really know that that's what happens. It's possible that if we got closer to 3 at 2.9999999 or something, some completely different thing happens. But from the information we have, and without having any other idea about this function, it's a reasonable guess to say that this is the case, that the limit as x approaches 3 from the left is equal to 7. This is a very awkward way to have to write it. Mathematicians don't like to write lots of words. We like nice, concise notation. Here's the notation for this concept. This says the same thing. The little lim, that's a limit. Underneath it, we have x approaching 3 from the left. This says the limit as x approaches 3 from the left of the function f of x is equal to 3. Again, just a guess. And in general, we have this pseudo definition, and I'll explain what I mean by that in a second. We'll say that the limit as x approaches a from the left of f of x is equal to L, and that's for any number a and any function f and any number L, if and only if the values of f get arbitrarily close to L as x gets close to a with x less than a. And so that is not actually the definition of the limit as x approaches a from the left, because look at all of the weaselly words in it. Arbitrarily close and close again. You know, what does that mean? What does it mean for a function to get arbitrarily close? What does it mean for x to be close to a? Is within a thousandth enough, or do you have to be within a millionth? So the answer is we don't know right now. But we're just trying to get the idea. We will come up with a firm and precise, careful, mathematically testable definition of this very, very soon. You won't like it, but that's okay. Right now, you just want to get the idea. The idea is, sure, it looks like that function that we were talking about a moment ago gets close to 7 as x approaches 3 from the left. And in a minute, we'll do the same thing from the right. It won't be surprising. It'll be just what you expect. But first, I'd like to consider, what do you think this function is? And so if you think about it for a second, come up with an idea of your guess as to what the definition of this function is. You know, pause the video if you have to, because I'm going to jump right ahead in a second. And here's a perfectly reasonable guess that most of you probably came up with. Maybe the function f is just f of x equals x plus 4. If you look at the 5 function values that we have, 2, 2.5, 2.9, etc., x plus 4 would work for all of them. 2.99 plus 4 is 6.99. And so that's one possibility. But it's not the only possibility. Here's another. This function also works. It's a piecewise function. F of x is x plus 4 if x is less than 3, and 87 times x if x is greater than or equal to 3. A completely different function that also gives exactly the right values for the 5 values that we've got there. And there are lots of others. You can do them just the way I did right here, or else you could, if you really wanted to, construct some horrible polynomial that went through all those 5 points, but then did crazy things as it got closer to 3. But we won't do that. That's a lot of work. But here are some possibilities. There are lots and lots of others. Okay, for the same function f, suppose I tell you that f of 3.1 is equal to 7.1. And that f of 3.01 is equal to 7.01. And keeping on going like this, suppose that f of 3.001 is 7.001, and f of 3.00001 is, etc., 7.0001. I might have left out an O there, but basically you get the idea. The idea is, as I choose x values that are closer and closer and closer to 3, but still to the right of 3, 3.00001, a lot closer to 3 than 3.1, the first one that I chose, it looks like the function values, the y values, are approaching 7 again. Make ourselves a little bit of room. Pretty fancy, huh? And this is the idea, again, just a guess, that the limit as x approaches 3 from the right of this function is also equal to 7. It's the same notation except with a little plus sign instead of a minus sign. That means we're approaching 3 from the right. These are both what we call one-sided limits. The first one being the limit from the left, the second one being the limit from the right. The limit from the right has the exact same definition as the limit from the left did, or pseudo-definition rather. Just change the x less than 3 to x, or x less than a to x greater than a, and it's the same thing, so I won't bother writing it out again. If there are one-sided limits, then there must be also something else, in particular two-sided limits. They are defined in terms of the one-sided limits. Here's the definition. We say that the limit as x approaches a of f of x equals L. There's the notation for the two-sided limit, the limit as x approaches a without any little decorative plus or minus near it. So that's a two-sided limit. So we say that the limit as x approaches a of some function f of x is equal to some number L, if and only if the limit from the left is equal to L and the limit from the right is equal to L. So both of those limits have to exist and agree with each other. They have to be the same value. And if that happens, then the two-sided limit is that value as well. If that doesn't happen, then the two-sided limit does not exist. And that's important, so I just wrote it down for you. If those two limits are not the same value, or one of them doesn't exist for some reason, then the two-sided limit doesn't exist. The only way the two-sided limit can exist is if the limit from the left and the limit from the right both are equal to each other, same value. Okay, we've talked about one and two-sided limits numerically and algebraically. We should look at some graphs and give you some graphical view of what I'm talking about. Here we have the graph of a function f of x. Let's briefly recall what this little open circle right there means. It means that at 4, the function value is not equal to 6. That open circle says this is not what the function value is right here. Instead, at 4, the function value is right here. It's actually 4. And at 8, the function value is right here. It's 2. Okay, let's see what happens as x approaches 4 from the left. Pick an x value to the left of 4, like maybe this one right here. What's the function value? It's this value up here. And then get even closer to 4, but to the left of 4, and you get this value up here. And get really, really close to 4, but still to the left of 4, and you still get closer and closer to whatever this value would have been right here. And it looks like as x approaches 4 from the left, the limit is equal to 6. So we would say the limit as x approaches 4 from the left of this function is equal to 6. We can do the same thing as x approaches 4 from the right, pick a value to the right of 4, like this one right here. You get a function value like that one right there, and then get even closer to 4 from the right, and you get some value over here. And as you get really close to 4 from the right, you start getting closer and closer to this hole here again, and we would say, once again, that the limit as x approaches 4 from the right of f of x also equal to 6. And since the limit from the left and the limit from the right are both equal to 6, that tells us that the two-sided limit, the limit as x approaches 4 of f of x, also equal to 6. That's our definition of the two-sided limit. Notice that it has absolutely nothing to do with the function value at 4. The function value at 4 is over here. It's equal to 4. And yet the limit from the left is equal to 6, the limit from the right is equal to 6, and so the two-sided limit is equal to 6. I'll say it again. The limits have absolutely nothing to do with the function value at the point that you're taking the limit. In other words, if we're looking for the limit as x approaches 4, either a one-sided or a two-sided limit, it has nothing to do with the function value at 4. That's important enough that I'll scroll it here. The limit as x approaches a of the function is completely independent of the value of f of x at x equals a. In other words, the value f of a. Okay, let's look at the limit as x approaches 8 from the left and the right. Again, as we pick x values close to 8, getting closer and closer to 8, but from the left, we get values that are getting closer and closer and closer to this value right here, which is 2, and so that tells us that the limit as x approaches 8 from the left of f of x is equal to 2. As we pick x values close to 8 from the right, getting closer and closer to 8 but staying larger than 8, we get function values that are looking like this and getting closer and closer to whatever this value is here, which looks like it's 5. And so that tells us that the limit as x approaches 8 from the right of f of x is equal to 5. And since the limit from the left is not the same value as the limit from the right, that tells us that the two-sided limit doesn't exist. Let's do one more just for fun. Why don't you try to compute the limit as x approaches 1 from the left and the limit as x approaches 1 from the right, and then see if there's a two-sided limit. Pause the video, I'll give you a second, and then we'll just do it. And you hopefully did the same thing. You picked values approaching 1 from the left, x values, and saw that the function values were getting closer and closer to 6. And so the limit as x approaches 1 from the left of f of x is 6. And as you picked values getting closer and closer to 1 from the right, staying larger than 1, it looked like they were getting closer and closer to that same value 6. That tells you that the limit as x approaches 1 from the right of f of x is equal to 6. And so the two-sided limit, the limit as x approaches 1 of f of x, also equal to 6 because the limit from the left is equal to the limit from the right. And in this case, it just so happens that f of 1 is equal to 6, but we know from what happened at 4 that that does not need to be the case. We don't need to have the function actually have the value of 6 at 1 in order for the limit to be equal to 6 at 1. Okay, that was the basic concept of limits. There'll be some homework on it, and take a stab at that, and then we'll talk about it in class if you have any questions. And see you soon.